The life and soul of all production is guaranteed quality. There are slogans in most factories stating defect reduction targets, but the ultimate aim should always be zero defects. The vital point to remember is that even if we only produce one defective product for every 10,000 produced, that item is still 100% defective to the person who buys it. POKA YOKE, or mistake proofing, is a vital factor in eliminating defects altogether.
Hello again, and welcome to Volume 2 of this three-part series on POKA YOKE, or mistake proofing. As I mentioned before, our goal is to achieve production with zero defects in an environment that is as harmonious as beautiful music. To do this, we must get to the source of the defects, rather than just catching defective products before they get to the customer. Let's bear that principle in mind as we take a look at the essential structure of mistake proofing through a variety of actual examples. If you carefully check defective products, you will find that there are basically two types. Those that arise during fabrication and machining, and those that arise in the assembly stage. The first type is processing defects, where some aspect of the fabrication of an article is defective. There are two primary causes for processing defects: processing errors and processing failures. Let's look first at some examples of POKA YOKE for processing failures. A processing failure means that the finished product has somehow missed one aspect of processing. This might be a procedure omission when one complete procedure has been left out, or an operational omission when part of a procedure has been skipped. In other words, these are all examples of incomplete processing.
Example 1. Preventing errors in the number of holes drilled. In hole drilling operations, it's often difficult to maintain the correct number of holes per piece of work, and sometimes too few holes are drilled. Before improvement, the operator had to do a visual check of the number of holes drilled. A limit switch was attached so that the number of holes could be counted automatically. Another limit switch that recognizes work placement was mounted on the jig, set so that a buzzer sounds if the work is removed with an insufficient number of holes. Notice how this mistake-proofing countermeasure focuses on the basic root of the problem, the number of holes drilled. Example 2. Preventing failure to remove flashings after die casting. In this example, the removal of flashings after die casting was sometimes neglected. Even though finished products were visually checked for flashings removal processing before shipping, unprocessed pieces slipped through the factory check. A mistake-proofing pin was set on the stand for the hole drilling fixture to expose unprocessed pieces before shipment, thus eliminating the problem. Example 3. Preventing skipping of the hole drilling step for bearings. In the manufacturing process for bearings, the workpiece is supposed to be cut and drilled before shaping. However, due to operator carelessness, bearings were sometimes being shaped before the holes were drilled. These operations were carried out depending solely on the care and attention of the operators, and that is why omissions in the processing order occurred. Pins were set in the die used at the shaping stage, so that it is now impossible to set workpieces without holes drilled in the appropriate spots. By doing this, omission of the drilling step in the manufacturing process has been eliminated. Example 4. Preventing failure to attach nuts. A nut has to be attached at the welding stage, but sometimes this stage was being omitted. The work and the nut were set on a jig for welding, but the setup was such that it was possible to do the welding without the nut. Mistake-proofing was implemented. Now, if the welding gun descends below the height of the nut to do the welding, a photoelectric relay is activated to make welding impossible. By doing this, welding without the nut in place has been successfully eliminated. Example 5. Preventing failure to carry out trimming. In this operation, untrimmed work was supposed to be on the left of the trimming machine and only trimmed work on the right of it. However, the operator sometimes mistakenly placed untrimmed pieces in the trimmed group, particularly as a result of working breaks. Untrimmed parts were only discovered in the pre-shipping check. A chute of appropriate dimensions was attached to the trimming machine, so that only trimmed work can pass down it into the trimmed box. Once this chute was attached, failures to carry out trimming were reduced to 0.
Now let's look at some examples of the other cause of processing defects, processing errors. A processing error indicates a situation where some expected process has mistakenly been replaced by another, or when some process has been done incorrectly or imprecisely.
Example 6. Preventing press die setting errors. In this example, because the guide pins for the press die forms were the same diameter, it was possible to set the top die on backwards, resulting in defective products and damaged dies. The diameters of the right and left guide pins were made a different size, and it has now become impossible to set the top die backwards. Example 7. Preventing faulty bridges. As shown in the diagram, when soldering the safety device parts of motors, there are 5 narrowly spaced points to be dealt with. Due to either lack of experience or poor concentration by the operators, it was not uncommon to create bridges of solder between the points. By modifying the insulators and placing dividers between the points, solder was prevented from flowing to neighbouring points. By doing this, faulty bridges were completely eliminated. Example 8. Preventing faulty hole drilling. When using this drilling machine, it was assumed that the drill always went all the way down when drilling holes. However, it sometimes came up too early, leaving a faulty hole. It was up to the worker's intuition to decide if holes were good or faulty. For this reason, faulty holes were sometimes discovered only at the assembly stage. Two limit switches were attached. Now, if limit switch 1 is released before limit switch 2 is activated, a buzzer rings to warn the operator of a faulty hole.
Work setting errors are another basic reason behind processing defects. So now let's take a look at some examples of mistake-proofing countermeasures for these types of mistakes.
Example 9. Preventing front-back and right-left attachment errors. Because there are no distinctive features in the workpieces in this example, they were frequently placed either backwards or upside down, leading to incorrect drilling. And since this type of error was usually not discovered until the assembly stage, delivery was considerably delayed, highly inconveniencing customers. Rather than depending solely on the operators to set the work correctly, mistake-proofing jigs were attached to prevent front-back and right-left reversal, so eliminating the chance of errors. Example 10. Preventing reverse setting of brackets. In this example, the case sides were symmetrical. When setting the brackets, the indented edge of the case was supposed to be placed on the bottom and the bracket inserted in the top. However, due to operator errors, the case was sometimes placed upside down and the bracket inserted in the wrong place. A mistake-proofing block was placed on the front edge of the jig, making it impossible to set the case upside down. The problem was eliminated. Example 11. Preventing tapping process operation errors. When the work was set in the jig at the tapping stage, sometimes it was not perfectly positioned. If this went unnoticed by the operator, the tapping was carried out incorrectly, producing defective work. The jig was modified by adding a mistake-proofing stopper plate at the rear, so that now, even if the operator makes a mistake, the work will be correctly set. Example 12. Preventing underside welding errors. When setting the work in the fixture, the operator was supposed to confirm that the bumps or knurls were on the top side. But even though the operator was paying attention, sometimes the work was set upside down. This meant that the wrong side was welded, resulting in a defective product. The fixture was redesigned to incorporate a mistake-proofing fixture which prevents upside-down welding. It is now impossible for the work to be set with the knurls facing down, and the operator does not have to worry about that particular problem. Defective welding has been eliminated as a result.
Now let's look at what we call product defects, where some problem has arisen during final assembly. The two primary causes are incomplete products and substandard products. Correctly made parts have not been properly put together, or they are missing. As the title suggests, incomplete products lack something. It may be assembly parts or accessories, or perhaps the instruction manual or other documents are not included in the packaging. We'll start with examples of POKA YOKE for incomplete products.
Example 1. Preventing failure to insert parts. In die casting, some of the inserted parts were often being neglected. As a first countermeasure, a special checking stage was established for the express purpose of confirming that all the inserts were included, and an inspected label was attached to the checked units. But insertion failures still occurred, and complaints that inserts were missing continued to come back from customers. A sensor to confirm the presence of all insertions was attached to the flashings removal press that is used in the step following die casting. If any parts are missing, the press is automatically stopped. At the same time, a light and buzzer warn the operator. By doing this, the original countermeasure to check for insertion failures was made redundant, and it was removed. Example 2. Preventing failure to mount E-rings. In this example, before improvement, parts were sometimes used in finished products which had not had E-rings mounted on them. The mounting of E-rings was supposed to be site-checked, but sometimes operators mistakenly attached a part on which the E-ring had not yet been mounted. Checking whether E-rings are mounted or not is no longer done visually. It is now done automatically, using an air cylinder and a micro switch to confirm correct mounting. Example 3. Preventing failure to attach nameplate. The problem in this case was that sometimes the nameplate was not attached to the product, due to some careless error or a break in the work process. The problem was duly noted and workers were encouraged to exercise more care, but no improvement took place. A photoelectric switch was set up to check whether the nameplate is attached or not. If it is not attached, a lamp lights and a buzzer rings. In this way, the problem has been eliminated. Example 4. Preventing failure to include all parts during assembly. During assembly operations, parts that were attached together as a set were sometimes not getting included. Their attachment depended solely on the careful attention of the operator. However, incomplete assembly easily occurred when the operators took a break or left the workplace for some reason. A special set of boxes was designed to prevent parts attachment failure. Each part is now taken out by pressing the cover of its individual box. This activates a limit switch and lights a lamp. When all of the lamps are lit, a stopper on the line is released, allowing the unit to move to the next process. By incorporating this countermeasure, failures to include parts during assembly have been eliminated. Example 5. Preventing incomplete packing of accessories. This is an example of packing problems. When packing products with which 6 accessories should be included, incomplete packing sometimes occurred. 2 workers were involved in the process, and it was divided into 3 operations. 1. Box assembly. 2. Cleaning of the main unit. 3. Packing of the accessories. But when the number of units inspected and ready for shipping increased, their work became rushed, and some accessories remained unpacked. Photoelectric switches were set up on the front of each of the 6 accessory holding boxes. Now, when one accessory is taken out, the light beam is broken and the switch is activated. The stopper will not go down until all 6 switches have been activated. When the correctly packed box passes the limit switch, the 6 accessory box switches are automatically reset. Another simple but effective example of mistake proofing in action.
Now we'll look at 3 examples of POKA YOKE for substandard products. Substandard products are those that appear to be complete at first glance, but turn out to include the wrong parts or the wrong color parts. In other words, there has been misassembly. Or for some reason they work incorrectly, or at substandard levels of precision.
Example 6. Preventing attachment of wrong parts. At a particular assembly stage, the variety of parts changed several times each day. This resulted in operators sometimes inadvertently attaching the wrong part. In order to reduce the time required for operation switches, parts not being attached were placed near the assembly line, and the operator sometimes mistakenly attached one of these to the work presently being assembled. As a mistake-proofing countermeasure, a rotating parts rack was designed with only one opening. By pressing a button for each operation, only the parts needed for that operation are rotated to the opening. Now it is impossible for the operator to mistakenly pick up parts for a different operation. Example 7. Preventing accidental inclusion of similar parts. In this example, the only difference between parts A and B is the diameter of a hole, 3 for A and 2.7 for B. For this reason, the 2 parts were often being mixed up. In addition to utilizing the 2.7 versus 3 difference in diameter in the countermeasure, a positioning hole was added to precisely fit the jig used in the assembly process. If part A, having no positioning hole, hits the guide, it cannot be set in that jig. If part B's 2.7 diameter hole hits the 3 diameter guidepost, it cannot be set in that jig. Example 8. Preventing accidental inclusion of similar products. In this case, the same metal mold was used to produce 2 similar-looking pieces, which were then separated after production. In the separating process, however, the 2 varieties often got mixed due to lapses in operator concentration. They were sometimes delivered to customers, resulting in complaints. The parts are now set on a jig and rotated 1/2 revolution. If the light from a photoelectric tube is able to pass through, it must be a part A. If it is blocked, that indicates it is a part B. The two very similar parts are easily distinguished in this way.
The idea of POKA YOKE is to create a system in which defects cannot be produced. We've just seen various examples of mistake proofing applied to the basic causes of defects. Let's now look at a ranking of the types of mistake proofing most often used.
The number 1 group of mistake proofing devices includes mistake proofing pins, blocks, guides and gates. They require no need for specialized knowledge in electronics or other areas. They're relatively easy to apply and costs are low. In second place are error detection devices. Limit switches and other sensors are used to detect deviations from standards, and then machines and facilities are halted and lights flash and buzzers ring to warn operators. This is a very orthodox approach to mistake prevention. In third place are the specialized jigs, which serve as regulators to ensure that even though an error occurs, flawed parts or products will be taken out of the flow of production. The majority of these are set up in such a way that flaws from previous production steps will be detected immediately at the next stage in production, as long as there is flow production. In fourth place are the counters and timers used to record production numbers. When results deviate from projections or standards, production is halted, and/or buzzers and lamps notify operators of irregularities. Finally, there is posting and checking, which operate under no specific regulations. They simply make use of human powers of concentration to reduce careless errors to a minimum. Checkpoints are written out and posted on blackboards, whiteboards and posters, and operational procedure checks are regularly carried out. Note that the 3 basic uses of mistake-proofing devices are for stoppage, control and warning, and they are used for both detection and prediction.
It should now be clear how effective POKA YOKE countermeasures can be in preventing defects even if there is human error. And we hope that the various real examples that we have presented so far have given you valuable hints in how to make improvements in your own factory. In Volume 3, we're going to look around the factory and examine various ways to introduce mistake-proofing measures. See you there.